Hello everyone, welcome to a problem session. So this is a problem kind of very interesting in the magnetic material problem. So if you know, they have a property called magnetization, and the magnetization means if I took a small volume here, then magnetic dipole moment there will be just m times delta v. So magnetization itself is magnetic moment per unit volume. It's kind of density magnetic dipole moment. Okay, so we have a uniform rod and we just kind of bend it, and there is a gap which is very tiny. So we have this gap, and gap is kind of related, is much less than the radius of the cross section, and much less than the length. So this approximation, I should say like this. So it's very narrow wire, so to say, and that's why we want to. This all goes into simplifying the calculation. The center is like that. Okay. Okay, we want to get at the center, so somewhere here. So what's going to be our strategy? Well, for magnetic material, you may know that you have a couple of concepts. Magnetization will lead to equivalent description of a current density. So you can turn magnetization problem into current problem, or surface density. So you can convert a magnetization problem into volume current and surface current density for the material. You can also go into what's called 1 over mu naught B equals to H plus M. So solve for H and you have solved for B. So how do you solve for H? So H has this del dot H equals to del dot minus del dot M. That comes from del dot B equal to 0 law. And del cross H is equal to J only free current flowing current, plus d dt, and this d minus polarization is equal to epsilon E. So if the material is polarized, electrically polarized, then that's so these are, we can use these two to solve for H and plug in there, and I got the B. The B is the regular magnetic field, and H is so-called auxiliary magnetic field. So that's one way to solve. So this is one way to solve, and this is another way to solve, and we can solve it both ways. Okay. So before we do it, let's solve it using this technique. Okay. So how would you go? So let's go technique 1, and this is technique 2. Okay. So here is a using 1, and we might just do it to at the end. Okay. So this is, we'll say this problem. If I fill this problem with a say this part, if I filled it with M, and the M that way, which same as that, and then M this way, I fill it that, if I can incorporate this in here, and then it's complete a full torus. full ring, and then I'll have a tiny ring to work with. So this together will be like a full ring, and this will be with W, but the magnetization is pointed down here. M is pointed down here, and M is pointed up here and is going around. M is pointed that way. Okay, so we're trying to convert using this. So problem become this, from magnetic field from this. So point P is there. We're interested in point P and point center of that. So we get magnetic field from here and magnetic from here. So how do we get magnetic from here? So we got a problem 1 and a problem 2, right? So let's do a problem 1. Problem 1, if I want to convert this into volume current and surface current. So if I put it inside, at a point inside, because M is changing in a direction of M changing, you can say the del cross M will not be 0, but because the loop is very big, we can think of it like a straight. Because of this, since L is very big, we can think of any small part as kind of linear itself. So the direction change has not much effect. So we can say for problem 1, we can say at any point inside, del cross M is roughly 0. So JB is 0. There's no current flowing here. There's no flowing current at all, but there's no bound current either. That means JB is 0. How about KB? KB, I have to go to the surface, at a point on the surface. Let's look at it here. Point on the surface. Point on surface. So at that point, magnetic field and magnetization is that way, and your normal is coming out from inside of the body to outside. So normal is coming out. So if I want to do like that, so you will get a current that will go here, and then so it will be a current going around. So so there will be, so you can consider this to be surface current going like that all around. So all around surface current. So this, what is the magnitude of that surface current? So you will have a M cross N hat, and the surface current will be, I'm just going to say the direction is shown, will equal KB will equal, have magnitude M, because they're 90 degrees to each other, and direction as shown. Okay, so I want to find out what the magnetic field at this point will be, at inside point. Well, using the symmetry of a torus, we can now use Ampere's law, right? So we will construct Amperian loop. So apply Ampere's law. So Ampere's law will give me, say this distance is little r. So that I go this whole, you can see the length, this will be approximately equal to the length of this. So this will be this B times L. approximately the length of this whole circle. I've drawn bigger. It looks like inner radius will give me different than outer radius, but because of this approximation, L considered very large, and the effect of the bending will be very tiny. And so this will equal to mu naught time I enclosed. What is the I enclosed? Well, you have a surface current and it's cutting through. So say you had a surface current. If you had a surface current going this way, then you will say let's look at the length of the line perpendicular to the current. So this will equal to K times the length of the line that's perpendicular to K, and which happens to be L also. So BL equals to mu naught, and K is equal to M. So M L perpendicular, and which is equals to M times L, and L got cancelled out, and B equals to mu naught M. Now the direction for the current tells me the B is up, it's in the same direction as M. Direction of B same as M. So they can write B from this torus is equal to mu naught M. So this one will give me B1 and this will give me B2. So I need to add this to get the net B, right? So B at P equals to this plus this. So need to work out the two. Okay, let me erase and come back. Okay, so this 2 has M pointed down, which means the current is, so this is a problem converting to current, has a K equals to M in that direction, and this L perpendicular to the current is equal to W. So this is so I is simply equal to a K times L perpendicular is M times W here in this problem, and so this is equal to a ring of current going in that direction, and that's equal to I going in that direction, and this is A. So magnetic field will be magnetic field will be pointed down opposite to that, and it will be equal to, how do you solve this problem? This you use the Biot-Savart law. So if you use that, you have mu naught over 4 pi and go around the current, where the current is I dl in the direction of the current cross unit vector. Say if you had this element dl, then r vector is that's r vector, and the unit vector is r, this is r hat, is r vector divided by the magnitude at r vector. So this is unit vector and the distance is square. So I need to do this integral around, and it's very easy. This is 90 degrees to each other, so it just becomes the length, and dl is just the radius. So this whole thing is very easy to do, and you get I is equal to remains I, and the dl is 2 pi a, r square is a square, and the direction is is in the down field, so it's in the down here over there, which is which is same as negative m direction. Now let's see. So this is I is mw, so this is mw. 2 pi cancels 2 and a cancel a square. So and m with the minus m, writing all this in vector form, mu naught w over a m vector. So this b2 is this, divided by 2. There's a 2 here. Okay, so we got the answer. This one was mu naught m, and this is mu naught w over 2a m. And you can just say, you know, mu naught m can be taken out, and it's a 1 minus w over 2a. And this, you would say, we'll get a negative value, but it actually won't get a negative value because of w is much less than a. So this will always be much less than a. So it's going to be pointed up because of narrowness of the this gap. Okay, so we did it one way. How do we get actually to get this thing using this is very easy actually, and I will illustrate B1 using second technique. Okay, so this is our answer, and we want to show that this is we did it the hard way. We did the torus and the Ampere's law. It's very easy to do it other way. So we found out that in here there is no free current, freely flowing current. There's like a battery or no source or anything. So this is equal to 0. So in here we see, and there's no electric thing, so we del cross H is 0. Now m is constant, so it's not diverging away, and so we know del dot m. Here there's a little bit divergence. If you want calculate that out, because it's you might say it's circulating. So, but m is constant, so this is also 0. So del dot H is also 0. So when you have a vector field where you have curl is 0, and divergence is 0, both of 0, this you can say only happens H is 0. Okay, or constant. You know, if you put a H constant, this will give you 0 and this will give you 0. So the boundary condition here will give you H equal to 0. So when I plug in here, what do I get? So we get 1 over mu naught B equal to 0. So we are talking about all of this in this situation where the whole thing is completely closed up. That's why we had a boundary condition 0. Okay, so when you have this, I'm sorry, 0 plus m. So this is talking about B inside, right? At point inside. So B is just equal to mu naught m, and that's the situation. This is easier, more direct, but a little bit more mathematical. However, sometimes it's helpful to do this. And in the future we're going to do problems just where we're going to use this. As a matter of fact, the next problem will be using that. I'm going to stop here. I hope you learned something from this. If you learned something from this, please subscribe to this channel so that you can get more from this kind of content. You like this kind of thing, you can hit the like button, and you can also check out my website. Okay, take care. Bye.